Welcome to Go Get It. Today we are going to discuss the third phase of any compiler design, that is semantic analysis phase. So this semantic analysis phase is nothing but with respect to the semantics of the programming language, whatever you are writing. So when we talk about semantic analysis, the very first thing comes into picture or comes into mind is semantic errors. So semantic errors. So what are the categories or what are the types of semantic errors we see in our daily life? So being a programmer or when you write a program, you need to stick to certain principles or certain set of rules which are associated with that specific programming language. So for example, one of the semantic error we can see here is incompatible type expression. So what does this incompatible type expression means? So let's make use of marker here. So what does this incompatible type expression means? So it's nothing but say for example you are using int in your program. So it is a very common type used in across the programming languages, say for example C, C Sharp or C++, etc. So instead of int you are using some say for example integer word finally you are using instead of int. So if you are using integer, so this complete keyword is not recognized by any of the programming language as far as I understand, or there may be any programming language. So if we consider C or C hash into consideration, then integer, that doesn't exist any keyword or any type which gives you integer. So we have int keyword. So incompatible type expression. So these kind of errors where we don't have the type compatibility. So in that cases, semantic errors are generated, and semantic analysis phase plays a very important role in determination of such errors. So the very next type of error is variable usage without declaring. So it's like, say for example, you have an addition program and you have declared int a equals to 2 and int c or int result. You have two variables and you are using it as a plus b. So here res or result and a are declared already, but b is not declared. So you will definitely get a compile time error or compiler error, which will state that b is not declared or b is not defined anywhere. So variable without usage without declaring is again comes under the semantic errors or semantic analysis errors. So likewise we have redeclaration of same variable in same scope. So this is also as the statement states, we cannot declare the same variable again in the same scope. Then scope violation is there. We cannot, we have certain limitations or certain limited scope for certain variables which are defined inside a function. We cannot make use of those variables outside a function. So those comes under the scope violation, and then mismatch of actual and formal parameters. So these are some of the semantic errors which are generated through semantic analysis. So basically semantic analysis phase dealt with attribute grammars, or we also call them as syntax directed translations, SDTs. So what happens in SDTs, what are SDTs first of all? So semantic directed translations are nothing but they are the representational formalism in which CFG production is attached with semantic actions. So this is nothing but one of the CFG action or one of the production which is attached with certain set of semantic actions. So these are called as semantic actions, and this complete set are called as semantic directed translations. So what happens is whenever this executes this production compiler, so it will have certain semantic actions that what it needs to do. So programmer will define or the compiler designer will define what it should operate or what should it do when this set of production is executing. So for example, here we have if of even dot type. So the type of this even is equals to e2 dot type. So the type of even and e2, if it is equals and even dot type is equals to integer. So and even integer is equals to integer, then the resultant values type will be integer. Otherwise it will be an error. So this kind of semantic rules or semantic actions we will define so that errors will be generated. So if, for example, when you do addition of two numbers, say for example, or let's consider the problem where we need to add. So say basically you will do 2 plus 3 that gives you 5. So here 2 is integer, 3 is integer, but you cannot do, or your programmer will definitely throw an error when you do this operation 2 plus a. This will definitely gonna lead to error. So this this validation or these validations are handled in this situation. So you can compare here. We are comparing e1 dot type, which is e1 is nothing but 2, say for example, and e2 is nothing but a string or a character. So this doesn't it fails here, it will directly go to the else and it will print error. So that's how compiler design work, or the semantic errors are thrown. So this complete grammar is shown here with certain semantic actions, and this complete set is called as SDT, Semantic Directed Translation. So this specific SDT, so for example we have an expression, say 3 plus 3 in brackets is equals to 6, and or another and say for example, and we have another expression called 3 plus 3 equals to 6. So this complete this one 1 and this one 2. So out of this two, which one is accepted or which won't throw any error in this case? I mean, whether this will be accepted or it won't throw any error while executing this production or this particular SDT, or whether we will check whether 3 plus in bracket 3 equals to 6 will throw any error. So let's draw the parse tree for this specific thing. So we have, say for example, we'll do the bottom up approach. So we'll write 3 plus, and in bracket we will write 3 equals to 6. So now this 3 will give you e dot type. This plus will go on the upper sides. So again this complete. So this 3 is nothing but e dot type. So this can be calculated from here. So 3 is nothing but the number. So you can see this production e gives num. So e gives num. When this executes, it will give you e dot type equals to num dot type. So e dot type. So we can write here that e dot type will give you e dot type is equals to integer, as 3 is nothing but an integer. Again 3 equals to 6 in bracket. So we have this situation here. So this is nothing but, this complete expression is nothing but a boolean expression. So inside this will get executed. So e dot type is nothing but e1 dot type. So we can directly write here as e dot type is equals to bool. So this is the expression, or this is the reduced form. We have plus here. So what we are getting here is e gives you e1 plus e2. So we have e, say consider for example this one is e plus e2. So we have this one as e2, this complete expression as e2. So if e1 dot type, so here we have e1 dot type equals to integer is equals to e2 dot type. So equals to e2 dot type, which is not equals. So we can say here that this gives you e, and here it will throw semantic error, because e1 dot type is integer and e dot type, or e dot type integer and e dot type is bool. So integer is not equals to bool, is not equals to a boolean. So this is wrong and this will throw error. So that's how we the compiler decides that 3 plus in bracket 3 equals to 6 is invalid, or it throws an semantic error. So logically, if you see this expression also, by looking into this expression, you can directly say that this is an integer variable and this will give you true or false. So 3 plus true or false definitely gonna throw error. So that's how compiler designer writes the code, and that's how it throws the error. So if you validate this expression 3 plus 3, and if you validate against this, you will get the answer as it is accepted using this SDT. So moving ahead, we'll have one more problem here. So here we have this SDT given. We need to evaluate or e.val for 2 hash 3 and &5 hash 6 and &4. So in today's none of the programming languages has such symbols used as an operator. So say for example, in future or currently a hypothetical situation that we have certain programming language where hash is used and ampersand is used as some of the operator for doing some operation, say for example addition or a multiplication. So that's how it is defined here. So E gives you E hash T. Whenever this production executes or this production is encountered, it will execute the operation of multiplication here. Similarly, when ampersand is encountered, it will execute plus. So that's how it is defined. So we can make use of hash instead of multiplication and ampersand instead of addition. So so we'll calculate this problem was asked in GATE 2004 also. So we'll see how to solve this problem. So we can draw the parse tree here directly from the given grammar. We have E, we have hash, we have T here. Again, this E will give you hash and T, and this T can give you, and mind well this is T, it is not E, it is T. T gives you T and F. So again we can write T and F. Then this E will give you, this E can be reduced using this T, and T can be reduced to F, and F can be reduced to num. Then finally we can get this T as T and F, and finally we will get that T as F and this F as num. This will be num. So if you input this programming in the given expression here, you have here 2. Here we are inputting 3. So 2 hash 3. This makes your first statement 2 hash 3. And then it will give you here as, this will give you 2 here, and this will propagate here 3 ampersand F. F is nothing but again, so 3 ampersand here will get as 5. I'm going correct, I suppose, yes. So this will give you 5 here. So this is 2 here, already we have. So 3 and F. So whenever this program executes here, so 3 and F, so T.val becomes T1.val plus F.val. So we have T.val as 3 plus F.val is 5. 3 plus 5 will give you 8 here. So this will give you 8, and again the next symbol we have is this T can be reduced to, let's write it here, F can be reduced to num, and F can be reduced to num. So ampersand we have, so we can directly write here 6, and this is 4. So this will be 6, this is 4. So this T ultimately will give you 6 ampersand F is 4. 6 ampersand 4, T.val becomes 10 here. 6 plus 4, 10. And here we have already 8. So 2, 8. So what is happening here is 2, I mean, we can execute this production here. E gives E hash T, which will be a multiplication operation. So we have 2 here, 2 into 8. This will give you 16 at, because E.val, that means this E.val becomes 16, and this is a hash 16 into T.val, which we already have as 10. So therefore E.val becomes 160. So we have answer here as 160. So that's how semantic analysis phase works. So these are the two problems I wanted to discuss here with respect to semantic analysis. There are few problems which we will be discussing in our continuous or will continue in our next session. Please watch the session, upcoming session on the semantic analysis phase. Thanks for listening. Subscribe for more videos. Have a great day. You can demand your needs at this email ID, demand@gogetIIT.com.